And hopefully my microphone is doing its job. Maybe it doesn't. Sometimes it doesn't work. So I'm going to just go through this fairly straightforward, fairly quickly. This entire PowerPoint is review. You've seen everything in this note either in grade 10 or previously in this course. So we're just kind of all gathering it together under acids and bases, because we've talked about naming acids, and we've talked about how acids start with H and all that type of stuff, and bases have hydroxide, and that's what this is all about. It's also a review of things like reactions of acids. So I've got some sodium hydroxide here, some hydrochloric acid. I've got some litmus paper. I've got some phenolphthalein. I've got some universal indicator. I'll save that for later. Little piece of magnesium and a little bit of baking soda or sodium bicarbonate. Okay. So I'm not going to, it's not going to be one of those where we're doing stoichiometry or where I'm asking you guys a lot of questions. I'm just going to burn through this quite as quickly as you guys can write, because like I said, it's very much review, and then I'll leave the rest of the class. You can work on whatever in order to prepare. So Monday is the review, and then Tuesday is the test. And I've pushed out the questions for the review, right? I put them on Google Classroom just maybe 15 minutes ago. Okay, so acid and base theories. Today we're going to learn about what is called the Arrhenius theory of acids and bases. And then on Wednesday, I guess after the test, we will learn an alternate theory, which is actually a better theory, called the Bronsted-Lowry acid-base theory. Before we do that, we're going to write down properties of acids and bases. And we've written this before. We wrote it when we talked about naming acids and bases, but it doesn't hurt. Good to write down. So all acids taste sour. I'm not going to taste the hydrochloric acid. It's too strong. That would cause a burn on my tongue. I'm definitely not going to do that. But according to the theory, it should taste sour. Vinegar, lemon juice has got citric acid in it. Ascorbic acid. That's actually vitamin C. That has a sour taste to it. They change the color they change indicators a characteristic color. So I put a little squirt of hydrochloric acid here on this watch glass. And if I take some blue litmus paper and I dip it in there, does anybody know what the blue litmus paper becomes when I dip it into an acid? Anybody remember the color that it turns? Yeah, it turns red. So we've got red litmus paper, we've got blue litmus paper. In actual fact, it's the same paper with the same chemical. It's just one is in an acid form and the other one's in the base form. So this blue one's in the base form, and if I dip it in there, it turns pink, ooh, ah, or it turns red. So we're going to write that down just to add to this, that litmus is red, and another important indicator that we're going to use in an experiment a little later on is phenolphthalein. So there's some phenolphthalein there. So if I take the acid and I put it into the test tube, and I put a few drops of phenolphthalein. Well, this is the most anticlimactic demonstration because phenolphthalein is colorless in acid. I don't know if you remember from the previous year. If I take some base now, I got to watch my lids or I'm going to contaminate the world. If I take my base now and I put a whole bunch of base in there, I'm going to get a neutralization reaction, and eventually I can get it to go, well, pink. There it kind of disappeared. It means I didn't neutralize it completely. So I got to add a little more base. And there it's staying. So now I did neutralize it, and I've caused it to become the base color. And if I add some acid again, I can neutralize that. and I can get it to go colorless again, as long as I put the right amount in to neutralize it. And there it goes colorless, because I've now added an excess of the acid. And we could do that all day long. We could add base and it would turn purple, or however you want to call it, pink sometimes we say. And if I added acid, it would stay colorless. The same is true with the litmus paper, right? We always take the litmus paper, we take the blue one, we dip it in some acid, and then we throw it out, right? In actual fact, if I was like super cheap, I could say, okay, everybody, keep all of your pieces of litmus paper and put them out on a paper towel to dry, and then I could stick them back in the container, because now if I put some sodium hydroxide on that litmus paper and I give it a squirt, a nice squirt, squirt, squirt enough, I can turn it back to blue, all right? So the base turns the litmus blue, and the acid turns the litmus red. And in terms of the phenolphthalein, the phenolphthalein is colorless. Phenolphthalein. And it's strange, but I can spell that correctly. I think it's because of the so many English conventions that are broken in it, that for some reason it makes sense to me. It's a PH and then a PH. Oh, actually, oh no, I missed it. PHTH. Phenolphthalein. See, I missed it. It's PHTH. Anyway, phenolphthalein is colorless. I even did it wrong. I wasn't concentrating. Phenolphthalein. A PHTHLIEN. And I's don't usually come before E's. That's weird. But anyway, all right. They're electrolytes, which means they conduct electricity because they have mobile ions, and they have a pH below 7. Therefore, acids must have something in common. And so what do they have in common? Well, they can ionize and produce H+. So you can write that down. So acids are molecular. They're not ionic, which means they're all nonmetals, starting with H. They will ionize to produce H+. We saw the H+ yesterday when we were doing our, 2 days ago, when we were doing our net ionic equations, and we took those H+ off of the acids. That's exactly what we're talking about. We've seen the term dissociation. Dissociation means simply to separate. So ionic compounds dissociate. They're already ions. But molecules aren't ions to begin with. And therefore, when they separate, ions are formed. They're created. And therefore, we call it ionization. It's a little different than dissociation. And on the next slide, I'll explain in a little more detail why. So if every acid drops off these H+, it's the H+ that are floating around in the water that are responsible for the properties of acids. So when you put a little bit of vinegar on your tongue or on your fries and you eat the vinegar and it tastes sour on your tongue, and I don't know because we're now stepping into the biology world, something on your tongue, some kind of sensory organ reacts to those H pluses. Sends a signal to your brain and your brain says, ooh, that's sour. Okay? These square brackets are going to become important to us. We're going to see them more and more again. This is different than the square brackets on a Lewis diagram, okay? The square brackets on a Lewis diagram, if I have an H plus, the plus goes on the outside. We put the charge on the outside. So in a Lewis diagram, we put the charge on the outside, and the brackets kind of say, okay, I've got this Lewis diagram, but this whole thing has a charge. In this context, the square brackets means molar concentration of, all right? Okay, now, what did I just say there? We've just finished our section that learns on how to calculate C equals N over V. And we can have concentration of many, many different things. I can have concentration of whatever chemical I want to dissolve in water. So if I have concentration, if I have the molar concentration of sodium chloride, and I have the molar concentration of H plus and the molar concentration of sugar, it doesn't matter. That's hard to write every time to be different in terms of separating them out. So if I write C every time, it can be confusing. So instead of writing C, we put square brackets, NaCl. That would be the molar concentration of sodium chloride. So square brackets reads as the molar concentration of, all right? So if I dissolved some copper 2 chloride, the molar concentration of CCl2, all right? If I separated that out and just had chlorides, I would have the molar concentration of Cl minus. So that's just a different way of writing the C when we're speaking about a specific chemical. So the greater the molar concentration of H plus, the stronger the acid. So that bottom statement really just means the more concentrated these H pluses are, the stronger the acid is. So if an acid has a lot of H pluses in a small little volume, you don't want to spill that on your hand because those H pluses will react with your skin and you'll get an acid burn. But if you only have a few of those H pluses and the concentration is low, then it probably wouldn't burn you. So the square brackets down here, and I'm just going to add it down here, square brackets reads molar concentration of, all right? So the square brackets reads molar concentration of. So the more moles per liter of H plus, the more dangerous, the stronger the acid is. Okay? And we will be using that notation in this unit. And then we use it a lot in the grade 12 university because we talk about concentrations of different things and we have to express it. Okay? Let's just do a few little ionization reactions. All right? So just to explain here, and you don't have to write this down, if I had NaCl, aqueous, we've already seen this. We've done these. We did them a couple days ago. That's going to break into an Na plus and a Cl minus aqueous. Don't write that down. Now, what's the difference between an NaCl aqueous and an HCl aqueous? Let me explain. The Na and the Cl are already in their ion forms. They've already traded the electrons. Sodium came along, chlorine took the electron away, became chloride. So they're already ions. They didn't need to become ions. They already were. So they simply dissociated. They went apart. HCl is different. HCl, as a gas, looks like that. They share that pair of electrons. But as soon as it gets dissolved in water, the chlorine takes the pair, it becomes a Cl minus, and the H becomes an H plus. So to begin with, this wasn't ions, they're not ions. So therefore, this process has to form ions. Hence, it's called ionization. In the end, it looks exactly the same. It looks exactly the same. That looks the same as that. The difference, NaCl was already ions, didn't have to become ions, but the molecule wasn't. And therefore, this is called ionization. Okay? So there's a slight difference. Slight difference. And typically, the H is at the front. So this is nitric acid. This would be H+. NO3 minus, aqueous. We've seen this. We actually did that when we did some of our net ionic equations. This is a special one. This is acetic acid. This is the acid that's found in vinegar. It can be written in two ways, and this is the way in which it's typically written. Okay? CH3COOH. We actually drew that molecule way back when we did Lewis diagrams. That was the last one that was hard, right? And I went to see if people could draw it. We had quite a few people draw it in here. In this case, the last H is the ionizable H. It's different than the rest. So this H is the one that falls off. These H's are stuck tight to the C. So this becomes CH3COO minus aqueous with the H plus on the back end. Okay? You could put it the other way. You know, the order doesn't matter, right? It doesn't matter where you put the H plus and the other ion, but it just looks like they separate it there. Okay. So acids have these H's that when you dissolve them in water, the H's fall off. All right? Typically, it's the first H in the formula, except for acetic acid. All right? It's called ionization because, well, they didn't start as ions. They started as molecules with bonds, and then they formed ions. Again, I'm just kind of going, you know, at a decent speed. Is there anything else we want to? Do you have any questions on that? Does everybody have the data off of that slide? The answer to that is no. But because it's recording, I'm not going to let the world know who said no. Don't write the top part. That's dissociation. Yep, there's someone else, and I don't want to name them either. Are we good to go? Good to go. All right. All right, making acids. So this deviates from the way I used to do this lesson. I used to then go talk about bases and all this type of stuff. And then I would do a separate lesson on reactions and making acids. But now I'm just going to do it all on the front end. Now, acids can be formed in many different ways. But the most fundamental way is the reaction of oxides of nonmetals dissolved in water. I can't remember because it was a chaotic start with my split other class. Have I talked about Antoine Lavoisier to you guys? No? Have I talked about this guy a little bit? He's considered the father of modern chemistry, all right? So he kind of took chemistry, from almost being like alchemy, like magic, and actually did lots of important experiments that then proved that chemical reactions have to be taken in terms of the law of conservation of mass and all kinds of different things. He also originated what is called the oxygen theory of combustion. All right. So before Lavoisier, they thought that combustion involved some strange substance that had a very weird name called phlogiston. It was called the phlogiston theory. And essentially, when something burned, the fire that you see was this phlogiston leaving the wood, right? We now know that when something burns, it's combining with the oxygen in the air, okay? And so Lavoisier proposed this idea that when something burns, it's combining with oxygen, all right? Now, before Lavoisier, they didn't call this special gas that helps things burn, they didn't call it oxygen. It had some weird names. But Lavoisier proposed the name oxygen. And the prefix oxy stands for sharp or sharp tasting, all right? And gen comes from to generate. So the term oxygen comes from, it literally means to generate sharp tasting something. When you burn something like carbon or chlorine or fluorine or sulfur, and you get an oxide and you dissolve it in water, you generate sharp tasting chemicals, sour chemicals, okay? So he called it oxygen because when he burnt it with many of these elements, it created an acid, all right? So that's a little history on where the word oxygen comes from. So if I take carbon and I burn it and I get carbon dioxide and I put it together with water, I get carbonic acid. And if I take sulfur and I burn it in oxygen and get sulfur trioxide and I react it with water, I get sulfuric acid, all right? So acids are generated when nonmetals are burnt and then dissolved in water, okay? All right? That's why it's called oxygen. Okay. Neutralization reactions. We've seen these. I'm only going to do one. We'll do the easy one. The other one we need to balance with some 2s because you'll notice we've got a 2 there and a 1 there, but we'll just do the top one. We did neutralization the other day. No need to drag this out. Now, I haven't talked about bases yet, but I think we've got an idea on what a base is. It's got a hydroxide in it. And one of the main reactions of an acid and a base is neutralization. And like I said, this is nothing new. We've seen it. I think this will be the 3rd time we've looked at neutralization in this course. We're now just officially writing it down along with acids and bases. So when you have an acid and it reacts with a base, it produces water and a salt. We like to write it with water at the end, or I do anyway. That's kind of the way I normally do it. But when you write the definition, for some reason, they always write it this way. You probably had this written down in grade 10. So let's do the first one, HBr and NaOH. The Na is going to go with the Br. Now that's not table salt, but any ionic compound is technically called a salt. That name probably would have originated with Lavoisier as well. That might be even older than Lavoisier. Salts would have been around for a long time, the word salt. And then water is the other compound. And that one's balanced because everything's 1, 1, 1. Okay? The other day we did a net ionic equation. That's great. This is just stating a neutralization reaction. And I don't think there's any need to do the second one. Good to go? Good to go, good to go, good to go. All right. Second common reaction is an active metal with an acid. And again, let's just write down the first one, because the second one's going to be a no reaction. I wrote that down. Well, actually, you know what? Let's write them both down. Let's write them both down, because it kind of defines what an active metal is. And I've got a little piece of magnesium here. It's pretty pretty dirty because it's got a lot of oxide and probably a nitride coating on it. But we'll drop it into some acid and see if we get something out of it. Make sure I put the right stuff in the test tube. I'll do the reaction for, or I'll do the balanced chemical equation first. We saw this the other day. Magnesium will displace the hydrogen. It'll produce H2 and some magnesium chloride. And I think we have to balance that up, I think, with a 2. I think we did a net ionic equation for that one. An active metal is anything above hydrogen. So it's got to be above H on the activity series. Right? That's what we mean by an active metal, that it's more reactive than the hydrogen in order for the displacement to take place. So silver is not an active metal, so it won't do it. Right? But magnesium is. So if I take a little bit of the magnesium here and I drop it in there, and there it starts to bubble away, floats to the top, bubbles form. I could put my thumb on it and do a gas test and it would go pop, right? Remember in grade 9, maybe you might have did a gas test thing, right? Hydrogen gas would go pop. I'm not going to do that, even though it's fun to burn things. In a chemistry room, not just like in general. Like just don't go up randomly burn things. All right. So active metal and acid produce hydrogen gas. Reaction of a carbonate with an acid. I've got a little bit of sodium bicarbonate, so it just has to end in carbonate. That will produce water, carbon dioxide, and a salt. We've seen this. We've seen this reaction. This is a double displacement with a decomposition. And this is also your classic make a volcano for a science fair experiment. And if you've never done it, well, then I'm sure you guys grew up on some Disney Saturday morning cartoons. No, not cartoons, but Disney Saturday morning shows. I always found them very annoying. There was one that involved like twins living in a hotel. Or is that way beyond your time? Zack and Cody, have you seen it? Every annoying preteen Disney show will involve a science fair at some point in time, and it will go, the volcano will go horrifically wrong every time. It's their go-to sketch. There was a cartoon, actually I invoke the discussion of this cartoon, that was like in the early 2000s when my kids were watching it. It was awesome. It was called Recess. Anybody? Recess? Anybody? Do a video? Have you seen it? Have you seen Recess? Yeah, it's pretty good. Yeah. Anyway, it involves science fair and, of course, an exploding volcano, because that's what Disney does. All right. I just use sodium carbonate here and HCl. If you want to do some fun at home, safe chemistry, some vinegar and baking soda, the classic. All right. Make sure you do it in a jar that has a nicely tight closed neck, and then it'll fly right out the top. It'll be awesome. Okay. And if you really want to top it off, what you do is you, when you're a kid, and you put it in a little bottle. Okay, we usually use a beer bottle, and you put the vinegar, and then you get a cork. Then you shake the heck out of it, and then you put it on the ground. You run away as fast as you can, and then it blows the top off. It's like things exploding, but safely. Okay. All right. So you've done that before? Have you done that before? Vinegar, baking soda? No? Yeah, that's a good one. So again, double displacement. So I'm going to write this as H2CO3 because we're going to have the H go with the carbonate. Then we're going to get some NaCl. Are we suffering? Are we an earthquake? Because I don't think that's me. And in the end, we're going to get two of those. And then that, remember, breaks down into H2O and CO2. So that's that double displacement with a decomposition. Okay, and we saw that. And then this produces the carbon dioxide gas, which is the fun part of the decomposition. I think I need 2 of these to balance that up. Okay, all right. So any carbonate with any acid will have some kind of salt. In this case, it actually is sodium chloride, and then some water and some carbon dioxide. And I could demonstrate that. I'll put the next slide up again before I do that. That's just going to, I don't know if I can get it to come right out at the top of the test tube, probably. I'm not advancing yet by the looks of it. So we'll get some baking. Oh, I got to get my book out of the way. That would be terrible. I wouldn't put a rubber stopper in it in science class because that's dangerous. You should never trap a gas in a glass test tube, nor in a beer bottle, actually. But we did it. All right. Carbon dioxide gas. Again, you would have did that in grade 9. We would have taken a burning splint, put it in there, and the splint would have went out. Right? Okay. Bases. On that last lab where we were talking about how to test for water and carbon dioxide, I would have accepted that a splint goes out. But there are many other gases that'll put a splint out. Like any noble gas would put a splint out. It wouldn't, promote combustion. The best way to test your carbon dioxide gas is lime water. And then you put the gas in the lime water, you give it a shake, it becomes cloudy. Very few of you Googled effectively on that on the last lab. Test for water is something that is called cobalt 2 chloride paper. And cobalt chloride paper is normally blue. There's some cobalt chloride paper right there. And if water hits it, it turns pink. Some of you looked up copper sulfate. If it's anhydrous copper sulfate, it's gray. And if you put a drop of water on it, it becomes blue. That's another test for it. So if I put water on my cobalt chloride paper, it turns pink. Blue and pink seems to be very common for some reason in these tests. That's a coincidence, nothing special about it. So cobalt chloride paper turns pink in the presence of water. And that's the 2 things I was looking for on that lab. Bases taste bitter. Now, I always thought that caffeine was a base, which is what often gives coffee that bitter taste if you don't put sugar in it to kind of cancel it out. But I think I Googled it once, and I don't know whether it is a base. We don't usually ingest a lot of bases. I don't know why. Some people swear by brushing your teeth with baking powder, right, or baking soda, right, to whiten it naturally, right? And you can buy toothpaste that has the Arm & Hammer thing that says whitening toothpaste. It's bitter. Sodium bicarbonate is a base. So if you've ever, and this would be safe to do, at your house because it's consumable. You could taste it. It would be bitter. It has just a bitter taste to it. I'm not going to taste the sodium hydroxide that I have here because that's just dangerous. It'd be bitter. Change indicators, characteristic colors. So again, litmus is blue. If there's time, I've got a little video clip that I could show you that has a chemist explaining a different way to remember the colors of the litmus. I always go with base blue. They both start with the letter B. That should be easy. Base blue, and then acid is the other one. But if we get a chance to watch the video, it's quite entertaining. Phenol, phthalene. I got it right this time. Phenol, phthalene is, what color do we say? Pink? Pink? Yeah, pink. We're going to be doing a reaction called a titration reaction. It's a neutralization. And we're going to do this mixing until it becomes just nicely pink. And I showed you the phenolphthalein color when I added the base, and then we can make it go back. All right? There are other indicators. There are many, many other indicators that have slightly different jobs. These are the main ones that we use because they're very simple. And as you continue on in chemistry, you'll learn more about others. Electrolytes, which means they conduct electricity. They have a pH above 7, and therefore, if they all behave the same way, there must be some common feature in order for them to have the same characteristic. And that common feature is the hydroxide ion. Again, I know you guys don't usually, stop me too much on this, but if there's something that doesn't make sense, by all means, let me go. But this is review. Like everything we've done so far, we have seen, either in this course or in grade 10. Bases are ionic hydroxides. There are other types of bases, which is why on Wednesday after the test we will have to discuss a more complicated, more in-depth theory of the way acids and bases work, because there are other bases that don't involve hydroxides in their names. So we have to be able to explain it. Again, we've got the term dissociate. I don't have the definition for what dissociation is because we already know. It means it's already ions and they just have to go on their way. It is the hydroxide which is responsible for the characteristic properties of all bases. And again, there's our square brackets. The greater the concentration, the molar concentration of hydroxide, the stronger the base. So the more of it there's jammed into that solution, the stronger the base is. In terms of reactions of bases, they're not nearly as exciting as acids. Sometimes, sometimes teachers might say, oh, they're opposites, right? Acids and bases are opposites because they can neutralize each other, kind of like positives and negatives. They're not quite as simple as being opposites, because if they were opposites, shouldn't they somehow react with other things? You know what I mean? Like, could they react with non-metals instead of metals? And they don't. They don't behave that way at all. So bases don't react in the same way as acids. And so I don't have a big long list of reactions of bases. They can be neutralized by acids. That's about it. They can be involved in some precipitate reactions, right? They can form solids, but that's not very exciting. Okay? All right. Just a couple of examples of dissociation, and we've done this. So this is really, again, kind of review for what we're doing on our test, where if we've got a net ionic equation or a total ionic equation, I have to dissociate them. And so again, I'm going to have the Na plus aqueous, because that plus is already there. It's just kind of hidden in the compound, and then the OH minus aqueous. And again, there's that OH minus. In something like magnesium hydroxide, where magnesium is in group 2, or barium hydroxide, it will produce 2 hydroxides, just like we were doing the other day. And therefore, on a, again, I know they're not molecules because they're ionic, right? But we can use the term molecules. On a molecule per molecule basis, magnesium hydroxide would produce twice as many hydroxides because it's got 2 of them in it. Okay? Question? Yep. we're going to be calculating next week pH, all right? And I've got a pH scale right here, right? And yes, basic down here is higher than 7 on the pH scale, even though this is kind of upside down. There's my 14 down here. We got to be careful about describing twice as basic. If I had 1 mole of this put into 1 liter, okay, then it would produce 1 mole per liter of this, right? But if I had 1 mole of this in 1 liter, that would produce 2 moles per liter of this. So it would have twice as many OHs in the water, okay? But the pH scale doesn't work linearly like this. So to say twice as basic is hard to say. All we can say at this point is it would have twice as many hydroxides in terms of concentration. The pH scale is what is called a logarithmic scale, so it actually wouldn't affect the pH too greatly, and we'll get to those calculations later. All right. So I guess the question is, how do we quantify twice as basic? You know what I mean? That's a set of words that has different meaning and different connotations, whether we're talking about pH or whether we're talking about concentration of that. So we got to be careful with it. Okay. All right. How do we make bases? Well, I'm assuming that Lavoisier studied the nonmetals first when he generated or when he created the word oxygen, which meant sour tasting generating stuff. Because when metals are burnt and those metals are dissolved, bases are formed, and bases are bitter. So I'm suspecting he studied the nonmetal oxides first, like burning a candle or burning a piece of wood, when he decided to call it oxygen. Because in the end, if you burn the metals, because you can burn metals, and I can burn magnesium. Actually, that's not a bad little demonstration. Wonder if it'll work. How many more slides have I got left? 2. I'm going to get to the end of the slides. I'm going to stop my PowerPoint, and then I will take some of that magnesium that I had. Do I still have more? Yep, right here. I'll burn some of it. I'll put it in some water. I'll see if it makes it basic. It should. I hope it does, because I say it right there on the note. I don't know if I can do it with carbon. I would need a carbon source. I guess I could burn a splint. I got a splint. We'll see. All right. How are we doing? Got her? Got her? Got her? Good. Just to talk finally about neutral substances. And I think that my next slide is just some homework on that. You bet. So just to talk a little bit about neutral substances. According to Arrhenius, and again, that's the name of the scientist who proposed this concept of acid and base. Neutral substances will dissociate, and it doesn't produce H plus or OH minus. If there's no H plus and there's no H minus, according to Arrhenius, it's neutral. Now, that's not always true. That's why the Arrhenius theory is not the best. You might think, why do we teach it? And it's because it's the simplest. It's the easiest to get into our brains to start the discussion on how this stuff works. This one. That produced more than what it was. Fun. All right, I should have brought these giant test tubes. They're okay, but sometimes they're too big for a particular demonstration. So if I have something like sodium chloride, when it dissociates, it becomes sodium plus and chloride minus, and that isn't an H plus, or is it a hydroxide ion? So according to Arrhenius, that should be neutral, okay? And it is. If I had sodium fluoride, though, it would produce an Na plus and an F minus, and if that dissolved in water, that wouldn't be neutral. So there's some of them that aren't. So the Arrhenius idea isn't perfect. Some neutral substances are non-electrolytes, so molecular. So if I took some CH3OH, that's called methanol, all right? And I dissolved it in water, it dissolves because it gets surrounded by the water. Remember, in the dissolving discussion we've had, the OHs can be attracted to the water molecules, but it isn't an electrolyte, and it's neutral because it doesn't produce OHs. You might say, there's an OH right there, Mr. Sanders. Why doesn't that produce OHs? Because that OH doesn't fall off. It is stuck way too tight to the C, and it has 3 H's on it right there. That hangs on when it dissolves, so it does not fall off. Okay, how do you know? These are all nonmetals, and therefore it's molecular, okay? Where sodium hydroxide is a metal hydroxide, it will dissociate. All right, the last slide is the homework problems and there's a worksheet, so some questions off the worksheet. The worksheet has problems on both today's lessons and Wednesday's lesson. When do you want to do this homework? You might want to try some of it today, and then you don't have to worry about it until Wednesday when we start talking about acids and bases again. Okay, so there's that, and I'm going to stop my